Hello, good day everyone, and welcome to the International Conference in Functional Materials and Civil Engineering in 2023. My name is Sajjad Mofarah. I'm from School of Materials Science and Engineering at UNSW Sydney, and my today's presentation is about how to develop functional materials and functional nanostructures for pseudocapacitance applications. Before starting my presentation, I would like to share my screen with you. Okay, so as I said, today's presentation is about design and development of functional nanostructures for high-rate pseudocapacitance energy storage. Before starting talking about different types of pseudocapacitance materials, I would like to talk about different types of energy storage devices. Energy storage devices, according to the specific energy density and power density, which is related to the time of charge and discharge, can be classified into three different types, I should say. So the first class can be supercapacitors or electric double layer capacitors. In this type of energy storage devices, we have low specific energy density, but also the charging time is very quick, and it can vary from few seconds to few hundred seconds. If you look at this plot that shows a specific energy versus charging time for supercapacitors, which is the blue line, if you change charging time to, for example, few seconds, that means actually you slow down charging time. There's no difference compared to when you have very quick charging process. That actually means that regardless of the charging time, a specific energy density of supercapacitors is low, and this is the nature of supercapacitors. However, for red line, which is related to battery materials, if you have very slow charging time, which is around, let's say, a few seconds, less than 10 seconds, you have very small specific energy density. And by slowing down charging time and giving more time to battery to get charged, you have higher specific energy density, and the energy density can actually go much higher than supercapacitors. So what this tells us is that for supercapacitors, we have low specific energy, whereas for batteries, we have very high specific energy. And where did this come from? For supercapacitors, or the other name for supercapacitor is EDLC, or electric double layer capacitors, because capacitance, or actually charging, occurs at the surface of the material, then that's all the surface contributing in charging of energy. And that's why there is no difference if you change the charging time. However, in battery, bulk of the material also involved in charge and discharge process, and by conducting slow charge and discharge process, charge carriers can actually have enough time to get into your materials during charging process, or to get out of your material during discharge. And that means when you have bulk involving in your charging and discharging process, you get higher specific energy. That's the difference between these two type of energy storage devices. And in between batteries and supercapacitors, or EDLCs, we have pseudocapacitive materials. We have pseudocapacitants that they have much higher specific energy compared to supercapacitors, but lower power density or charge and discharge rate. And they have lower specific energy compared to battery, but much better power density or charging time compared to batteries. So today's presentation is about pseudocapacitance, pseudocapacitive materials. And we have different types of capacitors here. So the first type is under potential deposition. In this kind of pseudocapacitance material, this deposition occurs when metal ions form and absorb monolayer at metal surface well above the redox reaction potentials. In this example, we have gold layer, which is a gold electrode, and then we have lead ions in the electrolyte that they deposit at the surface of gold layer. Why we're telling them, why we're actually naming them pseudocapacitor, because in pseudocapacitor, we have redox reactions. That means we have electrons getting involved in charge and discharge process. However, for EDLCs and supercapacitors, we have electrostatic interactions happening at the surface, and there is no electron transferring happening. So we should remember that for pseudocapacitor material, we have electron transferring in the reaction. The second type of pseudocapacitors is redox pseudocapacitor. Redox pseudocapacitance occurs when ions are electrochemically absorbed onto the surface or near the surface of material through Faraday charge transfer. So in this case, we can have capacitance from near surface layers. That means underneath layers, under the top layer, they can still contribute in charge and discharge process. And the example for these type of materials is ruthenium oxide that we're going to discuss thoroughly on the next slide. But the most interesting thing about this material is that we have hydrous layer across grain boundaries, and that's the reason we can get high capacitance. And the last type of pseudocapacitance is intercalation pseudocapacitors. And this intercalation pseudocapacitance happens when ions intercalate into the tunnels and layers of redox active materials, which is accompanied by Faraday redox transfer. And the good thing about this material is that there is no crystallographic phase transition happens. One of the disadvantages, one of the weaknesses of battery material is that we have phase transition happening during charge and discharge, and that is a drawback of batteries. And over a certain number of charge and discharge cycling, the material actually transform, and the crystal structure, we have phase transition in crystal structure, and then the battery dies. But for intercalation pseudocapacitance, we can actually go for higher cycling of charge and discharge without phase transition, and now we can actually have better cycling stability in our materials. So that's the difference. So on this slide, we are going to talk about ruthenium oxide, which is amazing. And ruthenium oxide was the first material that's with pseudocapacitance behavior that was discovered in 1971. The interesting thing about ruthenium oxide is that the storage is mainly because of protons of the electrolytes that go at the surface or near the surface, and they actually do Faraday charge transfer reactions at the surface or near the surface of ruthenium oxide. Despite the Faraday nature of the charge storage process, if you look at the cyclic voltammogram, the top in the middle figure on the top, which this is the cyclic voltammogram that we have to fill. In this one, the voltammogram has a kind of rectangular shape, and this is a typical shape for EDLCs. For the pseudocapacitors, we usually have one sharp peak in the oxidation part and one sharp peak in the reduction part. But here we have kind of EDLC behavior from ruthenium oxide, which is a pseudocapacitance, and that was very interesting. So this behavior comes from involvement of protons into charge and discharge process. The first report of pseudocapacitance behavior of ruthenium oxide actually showed very low gravimetric capacitance. The gravimetric capacitance was around like 100 or 150, and that's only 4 to 7% of ruthenium 4+. actually participated in the redox reaction. You know, in the future studies, then this capacitance improved, and the capacitance of over 700 Faraday per gram was reported. And there are many studies working on electrochemical behavior of ruthenium oxide and how this material has this interesting behavior, which is kind of electrochemical, EDLC type of electrochemical behavior, but it has a very high energy density. And ruthenium oxide ruthenium oxide hydrate with different degrees of hydration is the best candidate for getting such electrochemical behavior. And in general, ruthenium oxide hydrate materials, they have 4 unique features and properties that enable rapid Faraday reactions with very good high capacitance. One of them is that redox behavior of ruthenium 4+ is actually giving the Faraday energy density. The second one is that the good and the high metallic conductivity of ruthenium oxide, because it has a very good conductivity of ruthenium oxide, and that allows rapid electron transferring during charge and discharge process. The third one is because of the presence of a structural water in the system that enable rapid proton transfer, which is called inner surface. So this is also very important if you want to have a good redox pseudocapacitors when proton involved in the reaction. And the last one is a larger outer surface area that actually decrease diffusion distances. So in this slide, if you look at the middle figure, it compares electrochemical performance of ruthenium oxide as a film and a single crystal. And if you look at single crystal, if you look at the voltammogram of single crystal, it doesn't have similar behavior and similar performance as film, because the film is nanocrystal and it's hydrous and it is porous. And what it tells us is that how important it is to design the architecture of your material, to design the crystal structure of your materials, and all of these things can contribute in energy storage behavior of your material. So the bottom line in this slide is that we don't have redox pseudocapacitors and proton intercalation for ruthenium oxide, but we do have if ruthenium oxide is nanocrystal, is porous, and is hydrous. And this is all about how to design your material. So that's a very important thing. The drawback about, or the disadvantage about ruthenium oxide is that ruthenium is very expensive. It's around $2,000 per kilogram, so it's real expensive, and that makes these materials, kind of impractical or impossible for widespread applications. On the right side, we can see the crystal structure of ruthenium oxide, and on the bottom we have interactions of ruthenium oxide with water molecules. This has been obtained from the second reference that I cited on this slide, and it's about atomic scale analysis of ruthenium oxide and water interface under electrochemical conditions. That gives you valuable information about how water and ruthenium oxide interacts with each other under electrochemical conditions. All right, so we now understand about electrochemical behaviors, different types of pseudocapacitors, pseudocapacitor material, and we know that how important it is to design our material from the architectural points of view, and also this is because to maximize the exposed surface area. Here it shows different types of architecture for materials and how you can maximize the contact surface, because the higher the surface area, the exposed surface area you have, the higher interaction and Faraday reactions happening at the surface, and that means you're more likely to get higher energy density and also power density. So for many different candidates of materials like metal oxides or metal chalcogenides sometimes, and you have poor electrical conductivity. By designing the architecture of materials and by creation of defects in your system, you can somehow compensate poor electrical conductivity of your materials. We also have Maxim materials, which is a new material, and they have fantastic performance. They have fantastic electrochemical performance, and they are really good candidate for pseudocapacitance materials. In this slide, I'm going to talk about one of the works that we have done in 2019. It's published in Nature Com. And the very important thing about this paper is that we, for the first time, we showed that you can get the redox pseudocapacitance behavior from cerium oxide, which is which hadn't been published or hadn't been reported by that time. In this work, we have done fundamental electrochemistry on cerium oxide, and two things that we studied were, one of them was aqueous stability of different cerium species in aqueous solution, and the second was that how the second was design a Poober diagram for cerium oxide. So as you can see on this slide, A, B, and C shows speciation diagrams for cerium in different aqueous solutions, and how and what species is actually more stable at what pH. So that shows the concentration of different species as a function of pH. And in figure D, you can see modified Poober diagram of cerium oxide, and in which regions in which different species of ceriums are stable is shown. So this slide highlights the importance of fundamental electrochemistry and fundamental aqueous chemistry in understanding how to design materials to get different behavior that hasn't been seen and reported before. This is very interesting. This is a cyclic voltammetry of cerium oxide in aqueous solution, and we use the FDO substrate as working electrode for depositing cerium oxide at the surface. The very interesting thing is that because cerium has two oxidation states, C3 plus and C4 plus, the general belief is that we have one oxidation peak and we have one reduction peak, and they are not reversible, they are irreversible. But once we actually did cyclic voltammetry in aqueous solutions, different aqueous solution is very specific electrochemical condition, we actually got one peak from the oxidation part and two peaks in reduction part. That once we deconvoluted the big broad peak in the reduction, I'm talking about figure A, we got the yellow one, the orange one, and another peak underneath, which is colored in red. So two reduction reactions shows that we can actually have more oxidation. So during the second sweeping over oxidation, we got the second oxidation peak that we labeled as OX2. And then by increasing the number of cycling, as you can see from figure B, that we have that this is the voltammogram at 25th cycle, we have 3 pairs of redox reactions. The first redox reactions, which is OX1 and RA1, is related to the oxidation of cerium to CEO, is oxidation of C3 plus to CE4, but formation of CeOH4. That means like formation of cerium hydroxide and not cerium oxide. But because this experiment was done at temperatures above room temperature, I think it was around 60 or 70 degrees, we got cerium oxide, which is shown in red, OX2 and Ra2 that shows reduction of cerium oxide and oxidation of cerium oxide. So when we say reduction of cerium oxide, that means formation of oxygen vacancy. And that implies that if you have solid cerium oxide as a thin film on your substrate and you get reduction peak, that means that you actually form oxygen vacancy in your system. The difference here, the red shaded region and orange or yellow shaded region, is that when you oxidize C3 plus to C4 plus and form cerium hydroxide, this cerium hydroxide during reverse sweeping get back to C3 plus and gets back into the solution, and it's not stable at the surface. But when you have solid cerium oxide at the surface, it doesn't get dissolve back in the solution, and you have cerium oxide, and now you can create oxygen vacancy. And that was the biggest achievement in this paper, that we showed how to form oxygen vacancy using electrochemistry-based techniques. The blue shaded region shows that if you form oxygen vacancy in your cerium oxide, now you have proton intercalation in your system. And that is what exactly we can see in ruthenium oxide, having redox pseudocapacitance behavior because of hydrous layers across grain boundaries. And this is what we got when we made cerium oxide. So that was the first time that was the first report of showing redox pseudocapacitance behavior from cerium oxide. And we somehow used proton intercalation and deintercalation in order to get high capacitance. And this slide, we show that how a scan rate can affect the concentration, the formation of oxygen vacancy, and the concentration of oxygen vacancy forming. So in figure A, we deposited our cerium oxide using cyclic voltammetry technique at a scan rate of 50 millivolt per second. In figure B, we actually used 300 millivolt per second. We increased the scan rate, and then we increased the scan rate to 1,000 millivolt per second, and then we increased the scan rate to 3,000 millivolt per second. And the XPS results for cerium, for 3D orbital of cerium, and also for 1s orbital of oxygen, the results are shown here in figure E, I, F, J, G, K, and H, L. And these figures, these XPS results show that by increasing scan rates, you increase the concentration of oxygen vacancy in your system. All right, in this slide, I'm going to talk about one of the works that we've done in 2021, and it was published in Nanoscale. This work is about controllable design of defect-rich hybrid iron oxide nanostructures, and we had hematite as a precursor, along with carbon-based waste that we had, and we heated up the samples, hematite and carbon-based wastes, to 750, 850, and 950 degrees. And on the left-hand side, you can actually see the excited results. For 750 degree sample, the main phase is magnetite. For 850 sample, we reduced the sample to different phases, different polymorphs of iron oxide. But the most interesting thing is that we have two minor non-stoichiometric phases here. And this reduction is because of the presence of carbon-based materials that we had. The minor phases we had in this experiment, one of them was megamite. And as you know, megamite is the low temperature oxidation and weathering products of magnetite, and it has inverse spinel structure. And the interesting thing about magnetite is that it has a defective structure with 1/9 of the iron positions in the lattice being vacant. That is very interesting. In the second phase that we had in minority was non-stoichiometric Fe 21.34 or oxygen 32. And this non-stoichiometric and the magamide, they provided vacancies, iron vacancies and oxygen vacancies in the system. And the interesting thing is that Fe 21.34 or 32, that's a non-stoichiometric phase, it has electrical conductivity which is much higher than other types of iron oxide, polymorphs of iron oxide, and that improved the electrical conductivity of the whole system. So now we have a hybrid iron oxide with different polymorphs plus two non-stoichiometric phases we have. In Fe 950, once you increase the heating temperature up to 950, Woostite is going to become one of the major phases, and that's actually an issue because Woostite is not a good pseudocapacitor. All right, so as I said, the material we have was hematite as a precursor and carbon-based waste materials. Because we had waste materials, we had impurities into these materials, and one of the impurities was potassium. And during oxidation and during heat treatment, that potassium transferred to potassium oxide. And during rinsing sample after heat treatment, potassium oxide washed away from the sample, leaving behind perforates. So what you see from SEM images in this slide is perforated structures of carbon-based materials we have. And during heat treatment, we actually made perforated graphite and carbon-based materials. The very important thing about the presence of this perforated structure is that iron oxide can get trapped and can get locked into these perforates, and it can improve the charge transfer process and also electrical conductivity process, because as we know, iron oxide doesn't have good electrical conductivity, which is one of the requirements for energy storage performance. And by having carbon-based materials with close affinity with iron oxide, we can actually get very good electrochemical performance. This is confirmed in this slide, where in figure A on the right side, we show cyclic voltammograms of different materials we obtained, Fe 750, 850, and 950. And if you look at 850, the peak area is much bigger than 950 and 750. So 750, the peak area is very small. For 950, is much smaller than 850. And that means that by having Woostite in the system, it deteriorate the electrochemical performance. And by knowing that, you can actually adjust and tailor heat temperature and heating process in order to tailor the chemistry of your materials. Other tests that we've done, we've done cyclic voltammetry in different scan rates, and also we actually have a good comparative analysis in figure G that shows the superiority of these hybrid iron oxide materials compared to the other results that have been reported. Also, in the left side, figure A shows contributions to capacitive and diffusion contribution of materials, and how much of the capacitance we report is related to capacitive interactions that happening at the surface, and how much is related to the diffusion of charge carriers in the system. And according to that, by increasing scan rate, we have increasing in capacitive contribution. That means by increasing the scan rate, electrochemical reactions and redox reactions happening more at the surface than within the bulk or within the new surface layers. All right, in this slide, I'm showing the results of the electrodes of the two electrode configuration systems that we had. Figure A to figure D shows the results related to symmetric two-electrode defect-rich manganese oxide that we had, which was coated on FTO substrate, and it was tested in 2 molar KOH aqueous solution and at room temperature. In this scenario, we had a defect-rich manganate as working electrode, and the figure A shows cyclic voltammogram at different scan rates. Figure B shows gravimetric and areal capacitance as a function of the scan rate. So by increasing the scan rate, the gravimetric capacitance decreases, but it does not decrease significantly, which is a good point, and that means that charge and discharge can actually can be done quickly, and capacitive contribution is more than diffusion contribution, and that's why by increasing a scan rate largely and significantly, we don't see considerable changes in gravimetric and areal capacitance. In figure C, we see gravimetric and areal capacitances as a function of current density, and figure D shows a stability performance at a current density of 10 ampere per gram. The interesting thing about this figure is that we ran this in this test for 16,000 cycles, and after 16,000 cycles, the capacitance retention was around 90%, which is really, really high. And such a stability, great cycling stability is related to intervalence charge transfer occurring between the dopants, cerium and lanthanum we had, and manganese with multiple oxidation states. And at the end, we actually have, in figure E, we have the results of defect-rich manganate ultrathin fill in a solid state symmetric device. So we made this solid state symmetric device, and we actually used ITO-coated flexible PET polymer as a substrate, and we deposited defect-rich manganese oxide on top of this ITO-coated PET. Figure F shows the Ragan plots that compare the results that we obtained in this work with other values that were reported in other literature, and it shows that we actually have superior energy density and areal capacitance compared to other reports that were selected in this work, and also the power density is actually very good. Figure G, figure G shows that it's actually a camera image of the 2-electrode cell that we bended into different degrees, 45, 90, and 180 degrees. And figure H is associated with figure G, that we measured, we did cyclic voltammetry of 2-electrode configuration system at different angles and at different bending angles. And for all 45, 90, and 180 degrees, we didn't see any difference in the peak area, and that means that capacitance is stable while bending the electrochemical device to 45, 90, and 180 degree. So in my last slide, I want to highlight important factors in design and development of pseudocapacitance materials that we discussed over this presentation. One of them is microstructure, that how important it is to design your material from microstructural points of view, the morphology of materials. If you have 2D materials, if you have 4 to 3D materials, and all of these count when you want to design your material for pseudocapacitance applications. So the higher the surface area you can get, the higher the exposed surface area you can get, you're more likely to get higher capacitance. Because pseudocapacitance application is all based on redox reactions, so choosing materials with that have multiple oxidation states are suitable for these application. Also, you need to take surface chemistry into consideration, and what kind of and actually creating defects and engineering defects, especially at the surface, can improve the performance of your material. Also, heterojunction nanostructures, that we had an example in this presentation that was hybrid iron oxide that we made. The other important thing, which is fundamental, is aqueous and non-aqueous stability of your materials. It's always if you're doing pseudocapacitance performance, because it's electrochemical behavior, it's always good to do fundamental electrochemistry using a speciation diagram and Poolbit diagram to understand more about the stability of your aqueous stability of your materials and the species you would like to work on. And also about the kinetics of the charge and discharge. And sometimes you need to add material with high electrical conductivity in order to improve your electrical conductivity, because one of the weaknesses of oxide materials that we discussed thoroughly in this presentation is that they have poor electrical conductivity, and that can be compensated and that can be rectified, that can be addressed by adding graphene or carbon-based materials, or the materials having great electrical conductivity. Cycling stability is one of the most important thing, because when you're talking about supercapacitors, pseudocapacitors, and such materials that they have low energy density or compared to batteries, then power density is very important, and you got to have a very good power density, which is related to kinetics. And then that means you also need to have a very good cycling stability at very large number of cycling. So cycling stability is also very important. That means that your sample shouldn't be structurally, damaged, or it can actually stay for long cycling process.